Now let's take a look at exponential decay and the equation that goes with that. And what you're going to notice is that exponential decay actually doesn't differ a whole lot from exponential growth. So for example, let's say we have uranium-239, and we know that it has a half-life of about 2 years. So what that means is that a half-life means it's going to be cut in half. And so we can get that by multiplying by 1/2 or by multiplying by 0.5. Okay, so either one of those means half-life. And every 2 years, of course, that's the time that it's taking for a half-life to occur. So it takes 2 years in order for half of it to deteriorate. So suppose you have a substance of 1,000 milligrams. So there's our M value. That's our initial value. Determine the amount of uranium-239 remaining over the next 10 years. So let's start here. So the number of half-lives, remember we said, is every 2 years. So at 0 years, we haven't had a half-life yet. And so we would have that 1,000 milligrams. After 2 years, we would have 1 half-life, which means we would have 500 milligrams left. After 4 years, there would be 2 half-lives that have happened, which means we would have 250 milligrams. After 6 years, there would be 3 half-lives, which would be 125 milligrams. After 8 years, we would have had 4 half-lives, so then would be at 62.5 milligrams. And then after 10 years, that means we would have had 5 half-lives. We would have been at 31.25 milligrams. And as you can see, each one of these is decreasing by a half. So that's what half-life means, of course. And so what we are actually multiplying by then is 1/2. So this is half, whoops, can't spell today. This is half-life. 1/2 is our half, still can't spell, half-life. Okay, so let's see how this affects equations. So it has a half-life of 2 years, so there's our growth rate. It's not actually growing though, it's decaying, so we're going to call it a decay rate, so that's at 1/2. Every 2 years is the time that it takes for that to happen, and we started with 1,000 milligrams. So our equation is actually going to be the same, except now instead of where that was the growth rate, it's the decay rate. So M is our initial value, which was 1,000, times by our decay rate. So it's decaying by half, so 1/2. I'm going to put it in brackets just because it's a fraction. It doesn't really change anything, so don't get upset about that. To the power x, but of course now it's going to take 2 years for that to occur. So I'm going to put that x over 2. And that's what allows us to represent the proper decay rate, the time that it takes for something to decay. All right, so when plutonium-239 decays, it actually turns into plutonium-239, which is used in nuclear reactors. The half-life, so we're still talking about half-life, so that's at 1/2, is 24 years. So now our time's going to change a little bit. And let's suppose you start with 50 milligrams. So there's our M. Write an equation to represent this decay. So the amount is equal to 50 times by my half-life, so 1/2, to the, oops, x 1/2 to the x over 24. Okay, so that represents the x over 24. That's the time, right, that it's taking for it to occur. It's taking 24 years, so we have to divide by 24. Now, determine the number of years required for 50 milligrams to reduce to 5. Now, unfortunately, we don't have a way of kind of figuring this out yet. You will in grade 12. But now this is my A value. So A is going to be 5 equals 50 1/2 P over 24. Now we don't have a or X, sorry, I guess I use X. I should keep using X. So X over 24. So we don't have a way of kind of figuring out X quite yet. Once you see logarithms in grade 12, that will become easier. So instead, we're going to use like a systematic trial and error. But it's going to be more than just like randomly grabbing numbers. So if we started with 50 milligrams, I know after 24 years, I would be down to 25. So that's 24 years. And then this 25, if I go another 24 years, it would be down to 12.5. And then this would be at 6.25 after another 24 years. And then 3.125 after another 24 years. So I know if I'm looking for 5 milligrams, it must be somewhere in between here and here. So 24 plus 24 plus 24 is going to be 72. And if I add another 24, it becomes 96. So somewhere in between 72 and 96 years. So now it's just a matter of start playing with numbers to input into your equation and see if you can get it equal out to 5. So I would probably start by trying 80. 80 to me seems like a nice place to start. And so in my calculator, I would put 0.5 to the exponent 80 divided by 24 bracket equals, and then times that by 50 and see what I get. And I get, when I put an 80 in, so 50 times by 1/2 to the 80 over 24, I get 4.96. So I'm just shy of that 5 milligrams. I'm really close though. So then maybe I might try 81. So 50 times 1/2 to the 81 over 24. So 0.5 exponent 81 divided by 24 bracket equals, and then times that by 50. And I guess I moved in the wrong direction because I have 4.82. Oh yeah, so it's decaying, it's going down. So I should have tried 79. So let's try 79. So you see what I mean by it's just a trial and error, and you're just trying to get as close as you possibly can. Should have known that. It's decaying, so my numbers are going to go down the more the time that has gone by. 79 divided by 24 equals times by 50, and I get 50.1. So it must be somewhere in between 79 to 80 years that it would decay to, decays to 5 milligrams. All right, so just a systematic trial and error definitely to answer these types of questions if you're looking for an exponent. If you're not looking for an exponent, then you can just plug the number in and get your answer. But unfortunately, that one, finding an exponent is always messy. Okay, now one other thing I want to talk to you about today, not just decay, because decay is really the same thing as growth, so there isn't a whole lot different there. But I want to talk to you a little bit about negative exponents. So just in case you have not seen negative exponents in a while, or maybe didn't last year, I want to talk about it a little bit. So we know from our exponent rules, so let me just actually, let me go back a bit and let's talk about exponent rules. We know that if the base is the same and we're multiplying, then we add our exponent. So if I had like 2 cubed times 2 to the 4th, that would be equal to 2 to the 3 plus 4, which is 7. Okay? And then we also know that when we're dividing, that we subtract our exponent. So if I had 2 to the 7th over 2 squared, that would be 2 to the 7 minus 2, which would be 2 to the 5th. Okay, so division is subtraction, multiplication is addition. And then we talked about if you have an exponent to another exponent, that's equal to multiplication. So we just multiply those together. So 2 times 7 squared, 2 to the exponent 7 and then squared. You actually would just multiply those exponents together and you get 2 to the 14. Okay, so all of these you saw in grade 9, saw again in grade 10. And then we have what's called negative exponents. So negative exponents don't change anything that of these rules. The rules are still all the same. The only difference is that if you have a negative exponent, then you can make it positive by moving the term to the denominator. Okay, so notice the base doesn't change, it stays the same, but that negative exponent then becomes a positive. Same thing if you had a negative exponent in the denominator, you want to make it positive, it then goes up to the numerator. Okay, so we're going to be moving around some of our exponents in order to make them positive. All right, so now let's take a look over here. Consider this expression. So we are dividing. So we know when we're dividing that we're going to subtract our exponents. Start with your numerator and you subtract from your denominator and you get -2. And of course, we don't like to leave any exponents as negative. So I'm going to rewrite that as a positive. And it looks like this. Now I want to show you why. X cubed is the same thing as x times x times x, and x to the 5th is x times x times x times x times x. And we know from our rational expressions unit that we can cancel out factors that are the same in the numerator and the denominator. So if I do that, I get that, which means I don't have anything left in the numerator, so it's a 1. And then I have 2 x's in the bottom, x times x, which is x squared. So this is why our negative exponent rule works. What it's saying is when you get an answer that's negative, is that those x's actually are in the denominator. So that's where we can put them, okay? So evaluate each of the following. Whenever you evaluate, you first want to start by making them positive. So I'm going to start, that really should be 1 over 5 cubed. And then if I go to my calculator and I put in 5 cubed, I get, excuse me again, I get 1 over 125. Notice, not a decimal. So when we're evaluating, we always leave exponents positive and we always put things in as a fraction, never leaving it as a decimal. So here's the second one. Let's say you had 6 to the -5 times 6 to the 4th. So this is multiplication, which means we're going to add our exponents. So -5 plus 4 is going to be -1. So that's going to be 1 over 6 to the 1, which of course is just 1/6. Okay. And then we have -2 to the exponent -4 plus 4 to the exponent -2. So we're going to have to do these ones separately because their bases are not the same. So -2 to the -1/4 is going to be 1 over -2 to the power 4 plus 4 to the -2 is going to be 1 over 4 squared. Now, -2 to the power 4 is 1/16. If I put in -2 to the exponent 4, I get 16. And 4 squared is also 16. So 1/16 plus 1/16 is 2/16. And that, of course, can reduce to 1/8. All right. and the last one here, let's take a look at this one. We have division. So division, of course, means subtraction. So -7 minus -4, which is going to give me 4 to the -3, which is the same as 1 over 4 cubed, which is the same as 4 to the exponent 3, 64. Okay, so if we can remember that when you have your exponent that's negative in the numerator, it goes to the denominator. And still remembering all our exponent rules, we can evaluate these. Okay, so simplify each of the following. Write your answers with positive exponents. So we want positive exponents. Well, this is multiplication. So these are all being multiplied together, which means I'm going to add my exponents. So -3 plus a -5 is -8. -8 plus a -6 is -14. And of course, we don't want to leave it as a -14, so that's 1 over x to the 14. Okay, so we have different bases going on here, so we can only multiply together the bases that are the same. So it's very important. So when we do, what's going to happen is we're going to have a to the 4th times, so let me just kind of change this up, a to the 1, even though there isn't an exponent there, it's assumed to be a 1, times b to the -5 times b3. So I'm just kind of putting them all together, my a's and my b's. So we're going to add these together, which gives me a to the 5th. And we're going to add these together, so -5 plus 3, which is -2. Now, notice that this b to the -2 has a negative exponent. So the a to the 5th will stay in the numerator, but the b squared will go to the denominator where it becomes positive. All right, let's keep going. So we have g to the -7, h to the -2, g to the -5. So again, we can only put together the same base. So let's start with g. We're dividing here. So -7 minus -5. And then we have that h to the -2. And there's no other h's, so we're just going to leave it like that. This gives me g to the -2. H to the -2, and both of these are negative, so I'm going to write them by putting them in the denominator. All right. Okay, and last one for us to look at on this slide. Let's say that you have 2x, y to the -3, z to the -2 to the -4. So remember, when you have exponents to an exponent, then we're going to have to multiply. So even though this 2 does not have an exponent, we assume it's a 1. And even though that x does not have an exponent, we assume that's a 1 too. So what we actually get out is 2 to the -4, x to the -4, y to the +12, and z to the +8. So I multiplied all those exponents by the exponent that was on the outside. So that -4 touched all of them. I'm making a mess there, but it touched all of them. So you get the idea. Okay, so now I'm going to look here. Anything that's positive can stay in the numerator. It doesn't have to move. But anything that's negative, we're going to push that to the denominator in order to make my exponents positive. Okay, and the only last thing to do is to actually evaluate that number out. So y to the 12th, z to the 8th over 2 to the 4th, which is 2 times 2 times 2 times 2, which is 16, x to the 4th. And then we're done. All right. Just a few more. I want you to realize that if you have a fraction to a negative exponent, that's the same thing as that negative exponent hitting your numerator and your denominator. So now this has a negative exponent, so it's going to have to move to the denominator. This has a negative exponent, it's going to have to move to the numerator. And as you can see, all it really does is it flips your fraction. So a negative exponent on a fraction will flip the fraction. So just be aware of that. Okay, so same thing with here. We have x over y to the negative m. So that would be the same thing as y over x to the m, which is x to the m, or sorry, y to the m divided by x to the m. Okay, so the negative just flips the fraction. And lastly, just a third one now, actually with numbers to take a look at. So I'm going to flip my fraction. So 4 over negative 5, the exponent 3, which gives me 4 cubed over negative 5 cubed. I'm just going to put that in brackets because that cube touches the negative 5, not just 5. And I want to remember to put that into my calculator correctly. So 4 cubed is 64, and negative 5 cubed is negative 125. So there we go. There's our answers. All right, a little bit of notes just on exponential decay and negative exponents. So take a minute, pause this here, and feel free to copy this down. Just some important stuff that we've talked about. And then, of course, practice comes out of your textbook. Make sure you're practicing your decay, your exponential decay, and your negative exponents. And this will help us lead into our next section. Thanks.